that we wanted to connect this back to differentiation. We've already used the fundamental theorem of calculus. It seems like we should be able to use what we know about differentiation to help us evaluate these integrals. We've already been able to evaluate some integrals exactly, like using geometry. If it's a semicircle or if it's a trapezoid or something like that. But still, think about the fact that until today, you haven't really been able to resolve even a simple integral like the integral of x squared on the interval 0 to 2 or something like that without actually resorting to using your calculator or something. So after today, you'll be able to calculate that integral exactly without any approximation, among other ones. So the first notion we should introduce today is that of an indefinite integral. The ones you've been doing all along in all of last unit have been definite integrals. That's what in fact, it makes no sense to you before today to even conceive of this expression where we don't have any limits on the integral. So a good name for this would be like an indefinite integral. That is one that actually doesn't express the area yet at all in terms of the function. It doesn't actually provide for us an accumulation. And all we really mean is, by indefinite integral, we also mean well, I don't want to say yet. We want to kind of maybe come at this. I think you noticed in the warm-up the following. Let's see if I have it here. Yeah. Did you notice that no matter what C was, it looked like 3 problems, but originally really just one problem. You just took the derivative of a whole family of functions where C was any constant of your choice, and that was the answer to the warm-up. Now we've gone over it. Okay. So we call this function big F. We say big F is any function that we call it an antiderivative. This function, the cube root of 2x minus 1 plus c, for any c, that would be an antiderivative. There are many different antiderivatives for one function, but all of them differ by only a constant, right? It's a whole family of things that when you take the derivative of them give the function that you're interested in. Because when you run these things backwards. So this follows that almost immediately from the fundamental theorem of calculus. But we'll say more about that in a second. There's a lot to digest there. Is that okay? This is what we mean by antidifferentiation, or the indefinite integral. Same thing. We'll treat those as being the same. Is that okay? Questions so far? Am I right that you've kind of had a building suspicion that this is like what's going on here? I think we've talked already about the fact that these are like kind of inverse operations, the integral and derivative. But we want to make that like really explicit today. Okay, I guess I'll wait for that. We've wildly. Yeah. What's that?
So it's like finding a function from a derivative.
Yeah, exactly. Going backwards, exactly. Yep. Yep. So these will feel sometimes like a little bit of a puzzle. Wave wildly from you first. Albert, you good? See your pencil moving still.
Sorry, guys.
All right, so let's do some simple ones, see if you can figure it out. What's the antiderivative of 1? What is it that is to say that when you take the derivative would give you 1? Yeah, x plus any constant would give you 1, yeah? And just to show you the picture there, of course, just like we had a discussion in the first part of this course about, you know, hey, the derivative of a line is a constant. Well, let's also remind ourselves that the antiderivative of a constant function would be some line, right? If we're thinking visually on these. Let's go up a notch here. What about 2x? What's the I gave you 2x. That's a matter of convenience, isn't it? I gave you a nice one there. It's x squared, yeah. Plus a constant always, right? And of course, taking the antiderivative of a linear function gives a quadratic one. Again, as a matter of convenience, I'm giving you 3x squared. X squared is actually the harder one, right, to think about, but maybe you can consider that too. Yeah, x cubed plus c. It's easy to check that we're right by just taking derivatives over here and see that we're right. And of course, we get, you know, go up a degree on these. How about some slightly harder ones? What about x squared? What would the antiderivative of x squared be? Yeah, you need like you still want like an x cubed, but you need something there that's like ready to like kill the 3 when it comes down, right? Yeah, the 3's gonna come down, the 1/3's there, ready to like be like bam. And again, all you have to do is take the derivative to check and see that, of course, we're right. You know, it's easy as just taking the derivative. What about x to the 5th? In general, can you maybe make a claim here? Yeah. And then someone say what this would be for x to the n. It would be yeah, it's like the reverse power rule, right? It's the same, in fact it's the same as the power rule. It's just, you know, said with different indices, right? So there, we've just like established right off the bat within the first, you know, 5 minutes of our lecture, how to do this for every polynomial, and also more than that, also if n is some non-integer, you know, n could be negative or rational or something too. So let's do these, and by evaluate I just mean give the antiderivative, give the indefinite integral, and don't forget the c, right? So in a second, I'll call on some people to do them. Together with your properties of integrals, right? How are you going to handle this guy? Well, you can split it up first if you like, you know?
Well, yeah.
backwards on these? Feels like reversing the engine a little bit inside your mind. You're so used to differentiation. But Albert, give us the first one. Go ahead. Good. Don't forget the C. Good job. Max, second one. T to the 6 over 2.
Plus C. Oh,
Plus C.
Were you frozen?
Man, good job. Okay. T to the 6 over 2. Did you catch what he was saying? Why that works?
Yeah.
Technically, it's like 3 times t to the 6th over 6, but then he did the simplification for us without even batting an eye. All right. Give me C, Zachary, when you're ready.
Y cubed over 3 plus y squared plus C.
Yeah? Again, easy to check that someone's right on these by taking the derivative. Just do that afterward as a quick check, even if it's just in your head. And then D, Charlotte, when you're ready.
2a to the 3 halves over 3 plus b.
And again, whether you think she's right or wrong, let's actually try it. Like if you take the derivative of that, you get 3 halves comes down, the 2/3 is like there waiting to kill it. And we just get alpha to the 1/2, and the C goes away, so she's right. It might benefit you to, before you actually do the integral, to do pre-calculus first and write alpha to the 1/2, the alpha, and then write that as your second step. That is our final answer there, though. And then E, Vivesh, when you're ready. Say it one more time. -3 over x plus c. Verify that that works. You right? Again, it might be helpful to rewrite this before you do any integration. And just rewrite this as 3x to the -2 dx. And then now you can actually up the power by, what's the new power? -1, and then divide by -1. So that is what he did. Again, take the derivative to just check that he's actually right. And then Amy, the last one if you're ready. 3s to the 2/3 over 2 plus c. Again, just check her on that. 2/3 comes down, the 3 halves goes away. You get s to the -1/3, which is what we started with. The c goes away always. Yeah. How does that feel? You like this? All right. Still don't see necessarily why it's useful yet, but we'll get there. I promise. I should have asked you first, maybe on a couple of these. What's the antiderivative of sine x? Let's start with that one. What is it? Yeah, negative cosine. It's a little weird, right? Because the derivative of negative. Check it. Isn't the derivative of negative cosine? Of course, plus c. What about cosine? What's that going to be? That's an easier. That's probably the easier one of all these to sine. What about? Well, the other ones are a little weird. We'll have to wait for later to like take the antiderivative of tangent. But how about what's the antiderivative of? Oh, I don't know. Secant squared. Yeah. The other ones. These are a little bit. These are a little bit contrived, but there they are. Okay. So try a couple of those too. I mean, really, we can combine. These are things like we spent, like each one of these we spent a lesson on, or a couple lessons on, like getting used to these these forward derivatives. But like, I don't know. There's nothing really. We're just running them in reverse. So we'll just throw them at you one slide at a time. Lots of antiderivatives. Get it? And the reason for that is justifiable. We've already talked about it, right? This is the integral of c times f of x. So those all still apply here. Oh yeah, B's great, right? Yeah. Make a guess. I always say, kind of make a guess, and then correct it when the passing it. It's kind of it is a little big changes, right? In reverse. Like you know, when you take through it, like a 3 is gonna pop out. You should be able to walk away completely sure of yourself on these. Just take the derivative and check each of your answers as you're doing these. Likewise.
Bye, Rodney. You got it,
I think she stopped by his dad.
We used to be friends, not anymore.
How are we doing? You almost done with these? I don't want to rush. Let's start writing a couple of these up here. Ian, you want to give us the first one? Yeah, sure. Okay. I'll take it. Peter, can you take B? Say it one more time. Sine 3t plus c. Just take the derivative of each of these and check. The derivative of sine of 3t is cosine of 3t times 3, though, isn't it? Yeah, let's put a 1/3 in there. Does that fix our issue? Does that fix our issue? So there's actually kind of like a little bit of chain rule action having to be worried about there. Like that was a little problem solving that happened there. We didn't really talk about that. But now we have check. Let's move on. Okay. But you see how we can handle that situation? Joe. Someday. Do I have you in semester? Can I work on this budget?
Minus the sine of y plus.
What was the first one? Minus.
Plus 2y, negative 1/2.
Does it work? Check them. Don't believe anything you read.
Just one.
That's sine y. I think I like that. Negative 1/2 times 2 is, yeah. Is that what you were going to say? Over there? Does that work now? Negative 1/2 times negative 2 is 1. Good, I like that. Y to the negative 3/2. Okay, plus c. And then the last one there, if you can, Marcus, can you take it?
Give me theta plus c minus. Oh yeah, 3 theta minus c theta.
Yeah, I mean that's an interesting point. Do you need a plus like plus c1 and then a plus c2, like the two constants there? No, because like c1 plus c2, we can just call that c3 if you like, right? Throw it at the end. Okay, just do all the garbage collection at once with one constant. Yes, thumbs up on these. You love it. You love it. Okay. We'll save some. There are obviously other antiderivatives we'd like to be able to engage with later, but that's good. That gives us a good playing field to start with. Let's actually talk about how we can do definite integrals now using this technology. Like that was fun. That was a good thought experiment. But like, what does it mean for our lives? Here we go. So in our previous lesson, as in earlier in this slide, so this set, we talked about this. So I think what we mean is that if this is capital F in here, and this is little f, then we have this is true. And by the fundamental theorem of calculus, which we've talked about quite a bit, we have this. Then that means that for some c value, we have that this must hold. Like the things we've been coming up with on all these slides, the last problems we've done, are all just the accumulation function. Like that's what we've been coming up with for the appropriate choice of c. So do you acknowledge that this is true and this is true? I mean, because if you do, then I've just replaced blue with red. That's all. That's all, right? And this must mean that blue and red are the same. That's all. Try to color code it to make it nice. Kids these days. Some powerful pieces of logic on this slide. Let me know if you need a clarification. Yeah. Big F, yeah, to be clear, big F is, yeah, maybe I should use like a different letter because we've always used big F to mean like the accumulation function. But here I mean big F is any antiderivative of little f, right? That is to say, like big F is a function big F such that this is true, right? So it could be any, it's an antiderivative of little f. That is something that when you take the derivative of it, gives you little f. Good question. Give me another question. You have one? No, you don't. Thank you, Rebecca. Good. Yeah, so the question is like, for some c value. Now keep in mind that this c value will depend on where you start your accumulation from. Like you remember that one time where I was like, we did that warm up that I had you graph the accumulation function starting with, I think we started with like 1. And then I was like, oh wait, hold up, let's do the whole thing again, starting at 2. And then I was like, hold up, let's do it again, starting at 3. And the only difference you saw was a shift up and down. So that's captured right here in the algebra, isn't it? We're saying that the C value will be a particular C value. Well, I'm glad you asked. Let's see. Let's keep going. Yeah, it'll be for some C value. We don't know necessarily. Obviously, we need like some boundary condition. If we can just nail down one point on the function. All right. Do you acknowledge that this is true? It's like a thing we put up here once upon a time when we were doing properties of integration, right? Yes?
Should there be an imaginary box now? No,
There should not necessarily be an imaginary box. So if this is the case, we've just established that this right here is capital F, that is the antiderivative of little f, of b plus c. Track with me here, yes? Isn't that what we just, I'm going to go back to the previous slide for a second. I'll come back, I promise. Isn't that what we just said here? Okay. So if we have an integral of this form, like say from 0 to b, then this is just big F of b plus c for that one c value, whatever it is. And similar logic over here. Now, in the end, our choice of c matters not. So what we have here is, here it's in a box now. Oh no, it's not in a box. That's so sad. It's like part 2. It's almost an immediate consequence of, yeah, it's still sacred, but is the following statement, which kind of comes as a lemma to the fundamental theorem of calculus. We might call it the fundamental theorem of calculus part 2. Is this result, where big F, by big F we mean any antiderivative. Notice here that the C isn't coming into play, or I should say, if you want it to come into play, that's fine, but it will go away. Okay? This is the key to unlock how we can evaluate a definite integral now, using the technology we've just been talking about in the first half of the period today. So, the procedure will be, take your integrand, find an antiderivative, evaluate it at the top limit, evaluate the lower limit, and subtract. Again, I'll let you stare at that for a minute. Please, ask a question. So that's the thing. Huh? Yeah, there'll be many, many definite integrals now that we'll give you without a calculator. Yeah, we'll try to make them not intractable. By the way, there was a moment at a point in your life earlier this semester, just a couple weeks ago or whenever, when I did actually write this on the board, and and I was like, wait for later to. And the time when that happened was at the very last slide of our average value PowerPoint. Do you remember that? And it said, and we made this discovery. We're like, hey, there are 2 ways to calculate the average value of the average rate of change of a function. One was to do the function's value, like when we're doing velocity, we were trying to find the average velocity, I think, or something. And we said one way to calculate the average velocity is to do the integral of the velocity function. Do you remember that's how you calculate like the average velocity? Or the average value of any function? But we also said another way to calculate the average velocity of a function, the average velocity of a particle, from like algebra 1 is position here minus position here over b minus a, and of course that immediately implies, this is saying the same thing, isn't it? Forget the b minus a. Yeah? Do you remember that? And what's x in relationship to v? An antiderivative, isn't it? Isn't the position the antiderivative of the velocity? Okay, so x and v, whatever, big F and little f, same thing. Let's actually do it. Are you ready? Let's actually. This is an exciting time in our lives to evaluate some integrals by hand. We'll start with one. We'll start with one that you could have done prior to today using geometry. There's the picture. And I'll just skate over the details there because I think we've done this before. You know, it's a trapezoid, so 1/2 the height of our trapezoid you could consider to be like 4, and the two bases are 3 and 5.4. If you plug in 5 and 9, you'll see that that's the case, and you get 16.8. Let's also do this now using the antiderivative. The antiderivative of 0.6x is, or one antiderivative is 0.3x squared. Verify by taking the derivative. Okay, plus some constant. So if you evaluate this antiderivative at 9, you get this. If you evaluate it at 5, you get this. And if you subtract, and in practice we won't have that. We just won't use the c once we move forward from this. But I thought I'd show you that here we'll use the c for now, just to show you that in the end it doesn't matter. You get 16.8, or usually here's the work you'll just write. And we use this vertical bar that means, like in mathematics universally, not just in this context where we evaluate integrals. It means like evaluate this on that interval from 5 to 9. So we'll write this 0.3x squared without a plus c. It wouldn't be wrong to write a plus c, but we just don't, because all of us know that this is going to happen. We just usually don't write the plus c when we're doing definite integrals. From 5 to 9, plug in 9, plug in 5, subtract. So that's usually the compact way we'll write your work. You know. All right, the real excitement comes when we can finally do like one with like x squared, something we couldn't have done before. We're gonna move to the next slide when Zachary is ready. You're done? Oh, he's done. And then you're done too. You good with that? Please, stop us if you have a question about why all this works or why a certain number shows up in a certain place. Let me show this example. You can track with this on the calculator if you like, but these are the two pictures of the original function and the antiderivative. This is apparently what we just did: f of 9 minus f of 5, and that was like 16.8. Why did that work? Does it give you the same thing if you use like a different c value? You're like, of course it does, right? That distance is still 16.8, regardless of whether you move that up or down, right? You want to do another one? In all cases, this comes out to 16.8, regardless of what c value you use, right? right, we do need to do one of these at least before we go here. Let's see if we can do a couple of these here.
Okay.
What's the antiderivative? We're good at this now. 1/3 y cubed plus 2y. Again, you can just not have this, the c on the interval 1 to 6. So plug in 6. Plug in 1. And carefully obeying signs and distributing properly and doing all your arithmetic correctly, figure out what you get. Work on B and C while I pass out your homework. There are 2 worksheets that you need. There are 2 worksheets you need. Only Nick is allowed to eat. Whatever, you can do it on Monday. Everyone get both worksheets? Okay? And to be honest, I think there's probably more like 30 seconds or less per problem. Over there. Whoever after is kind enough to drink always I know you gotta go. Take it easy, guys. See you, Bill.